Hello, community. In order to increase the intelligence in artificial intelligence, we have to reduce its complexity. And you might say, hey, are you really sure about this? Yeah, just look at Anthropic, the latest we have. If we look at Anthropic, Cookbook, Pattern, Agent, Orchestrator, and the Worker, the interaction here of multi-agent system we see clearly. Imagine we have a human input like plan a small, casual weekend barbecue for friends. And we use now here the multi-agent construct, the code construct here from the cookbooks of Anthropic. So it's easy. We have a a central orchestration agent, yeah? And primary job of this agent, the central agent, is here to think and to plan, nothing else. So it takes here the simple human task here in yellow, inserts it here into the orchestration prompt and makes a single call to the LLM. And given now here the complexity of the pre-training dataset of this particular LLM, and you know an LLM is just a pattern matching machine, nothing else. Then we have here the code, and the code is simple. Return your response in this simple format, do an analysis, and do a decomposition into task. So this simple human sentence is now exactly executing this. You have here your Python notebook. You see this is exactly gonna happen where we have the analysis and the task, and you just follow this, and this is here the response if you do this. So you get in the analysis, hey, the user wants to plan a casual barbecue. This requires several different kinds of thinking. No, first, a creative part to decide on the food. Second, a social and communication part to invite the guests. And third, a logical organization part to create a shopping list. Breakdown, this ensures each aspect is handled well by a specialist. And for the task now, the LLM here, it's an Anthropic LLM, defines now 3 agents. A culinary planner to create a simple and crowd-pleasing menu, a social coordinator, causal text messages to send to your friends, and a logistic expert, what we need here, what we have to buy for the burgers, for the potato salad, and so on. And then we just turn here the LLM structured text, the output of our large language model, into a Python list of dictionaries that we can take care about it in our Python code. Simple. And then this is now the response here of the worker 1. So 6, great. So I make a new separate LLM call for the worker prompt, and worker 1 comes back now with the response, given here this information, says, great. So my job is to come up with a barbecue menu. And you have given me exactly the elements that you want, so here it is. The main menu is a classical beef burger with some brioche buns. Side is here a creamy potato salad, and for the drinks we have some homemade lemonade. Wasn't this beautiful? And after all the loops finish and the process method returns here a single dictionary containing here all the analysis and a list of all the structured results from all the workers, everything is, if you want, reported back here to the orchestration agent. And this is it. And then the orchestration agent has to decide. Do we have the whole information? Is something contradiction? Is there some problem? And now let's have a look at this. Now, you know, in my last video, we looked here, especially here in the research lead agent, in case we do some research agent here. And we analyzed here the user's prompt. So this means my human prompt now is now modified. Because Anthropic says, listen, what you have given us as a prompt, that's not okay. We have to analyze and break down the human user prompt in much more detail in order to provide a good solution. So this is what we had a look at, no? Anthropic will say, hey, identify the main concept, the key entities, and the relationship in the task that the user is asking me to do. List some specific facts or data points needed to answer the question well. Note any temporal or contextual constraint on the question. Analyze what features of the prompt are most important. What does the user likely care about most here? Oh, wow, this is an interesting question for an AI, no? Determine what form the answer would need to be in to fully accomplish the user task. Would it need to be a detailed report, a list of entities, an analysis of different perspectives, a visual report? What components does it need to have? So here we have hard-coded. This is the structure you have to take care. And you might say, oh, it's so beautiful. So the best LLMs on this planet, and I think, yeah, Claude 4 is one of those. They have a simple plan for their increased intelligence. They say, we take the human prompt, you know, this by, yes, our users, and we reduce its complexity by generating a lot of lower complexity tasks. Let's say up to 15 different agents, and each agent just gets one single lower complexity task, because otherwise we would not be able to solve the complexity. So, in order to increase the performance of the next AI generation, we have to break down everything into lower complexity tasks. And this process here of a complexity reduction through a decomposition is our current central design pattern for the next super intelligent AI. And you might be a little bit disappointed. You say, hey, this is interesting. So complete reductionism, and then we have to build everything up again, and there's just one agent who does this? Yeah, me too. I had a feeling that this will fail. So you can do the experiment. You say, hey, design a new laptop that is ultra lightweight, has all-day battery life, and is powerful enough for a professional video editing task. Ne? And the orchestrator agent now, the boss agent, ne, breaks this down into the specialist task, like we have in our human query here. Ne? We have a worker A, the performance team, select the most powerful CPU. Then the worker B and the battery team, choose a battery with the maximum possible capacity. And the worker C on the chassis team, design the lightest possible chassis and the materials like magnesium alloys or whatever. So you see, it is straightforward, but you understand that the complexity is not a complexity that you can break down simply in 3 elements. Because what the worker will do, it will proceed here in isolation and deliver seemingly correct, no? And you can do this experiment. The code is available for you for free, no? The worker A selects a powerful, hot, power-hungry Intel Core, whatever, and top-of-the-line RTX 5090 GPU with 8 GB or something like this. And then the worker B specify here massive 100 watt-hour battery, the largest legally allowed on airplanes, heavy, large, hot. And the worker C designs an incredible thin and a very light chassis that has a very little room for cooling or any larger battery, no? And then all 3 solutions are sent back to the orchestrator agents, no? And now this orchestrator agent has an impossible task. And this is because here, Anthropic here, defined here their specific research multi-agent system in this way, a hub and a spoke system. So we only have, everything has to go back to the boss, to the central orchestrating agent. We have no communication, no coordination task between the agents. So this will fail. This architecture will fail for sure. And the explanation is here. Let's have another example, yeah? Let's say, hey, let's develop a comprehensive launch strategy for a new AI-powered personal assistant, an app for the App Store or whatever. And now I just want to show you, whenever you decide on a specific LLM, you have to know what is this LLM specialized in. Because an LLM that has been heavily trained on textbooks, market research reports, financial statement, corporate strategy documents, and an LLM in the training data pattern, it found pattern to prioritize here profitability, competitive positioning, and really go for strict measurable return of investments. The analysis of this LLM will be in this particular way. No? Monetarization, unique value proposition, financial modeling to ensure the long-term viability. You understand immediately the revenue stream. And then it will decompose this complex human prompt into 3 subprompts like Anthropic tells you. You have to decompose this in 3 agents. You will have 1 agent for the competitive analysis, 1 agent for the monetization strategy, and 1 agent for phase 1 marketing campaign. Instagram, whatever, you know. Regarding cost per acquisition and everything. But you see, this is now completely different from any other LLM that has been trained on something else. So you see, whatever is your complex human task, the more precise you are, the more information you provide, the more background that what you expect the system to do, in which environment the system should operate, and the more information you have, the better. But all the AI companies, the global corporations tell us, hey, don't tell us how we should come to a solution because we hard-coded this into our multi-agent system. Just tell us what you want to achieve. So, careful when designing the prompt. Let's have another example. Another LLM. Another LLM was trained here on some design thinking blogs, some ethical AI manifestos, some psychological studies on human-computer interaction. We're talking now about emotion, trust, community building, delightful experience. And now the analysis. So for the absolutely identical code by Anthropic, we just exchange here the LLM. No? The analysis is now completely different. We have to build the strategy around transparency, a delighting onboarding experience, foster a sense of community from the very beginning. No? So you see, focus on human-AI relationship. So whatever it was in the pre-training structure of particular LLMs, you will see here really hard-coded effects and analysis. So be careful what you ask for. And then this LLM will have now 3 complete different agents. And also we have here in our prompts defined here by Anthropic, hey, you have to take, I don't know, maximum 15 agent, minimum 5 agent, let's say minimum 3 agent, and those are the agents that come back. The ethical guide rails and onboarding agent, a community and feedback loop agent, and a user journey content strategy agent. With those particular topics, those particular tasks that are now analyzed in further details by the multi-agent system. So you see, there's an extreme degree of freedom and redundancy here. Whatever LLMs you choose to decompose here, your specific human complexity, your simple task for the LLM, it is not at all a simple task because it is missing all the information. So the more precise you can be what you want to achieve, the more it is helpful for the AI. But just notice that this orchestrator agent is not a neutral task divider here, because it all depends on its pre-training. And if it had a training bias or some cognitive patterns here from their pre-training, this will now act as the founding philosophy of the entire project. So you can have an extreme bias given here specific pre-training patterns here in the very first training data. And I did some experiment and just that you see it here and said here for one orchestration LLM for a strategic goal is the most critical decision is really careful which LLM you take for your boss in a multi-agent workflow. Here on the left side, you see I chose here Claude Sonnet 4 and the Thinking 32 process, so the maximum of Sonnet 4. And I ask, hey, show me in my particular query, for how many tasks would you provide me now here a blueprint? And Claude 4 Sonnet 4 came back and I said, hey, 190 individual tasks and give you a comprehensive task list. Could be do project management, team assignment, time employment. Beautiful. And for the exact same prompt, from Gemini 2.5, the Flash, not the Pro, just the normal Flash, the old one, get back 155 singular tasks in a detailed decomposition. So the same prompt, the same structure, but watch out what LLM you use. The tinier the LLM is, and the lower quantized the LLM is, you lose a lot of idea generation complexity here. So careful here, choose the right LLM. So you see, a complex human task, and now there's some fun element because it is rewritten by AI, no? Of course. Like here, experiment with Amazon Nova Experimental JUT 0514. I have never heard of this model before. And Amazon rewrote my human prompt into 1, 2, or 3. Just because it was not satisfied. No, I did not provide enough information. So for Amazon to accept my human prompt, it rewrote the prompt in different options. So you see, it's fun to use AI. But it's even better because the rewriting doesn't stop here. So, as I told you, I have a complex human task and I go to an LLM or a mixture of expert system. And now what's happening in almost all cases, those LLM or those MOA decide to rewrite here my human task. Because the AI says, hey buddy, I don't like the way you formulated your query, no? Given my pre-training data sets and given my pre-trained pattern recognition system, And given my examples that I was trained on, I would like to rewrite your prompt in a prompt that is much nicer for me as an AI system. And we do this and we see this if your core is an LLM or a mixture of expert system or an agent, a prime agent, like the orchestration agent. But the fun doesn't stop here, because if you go here with the prime agent has two tasks. Ne? As I showed you, is the boss here. It designs here the planning phase for the solution, for the execution of the deep research or the deep thinking process of a multi-agent MA system. So given here that it designs the task and the analysis and the background knowledge and the context and examples that it knows of, this is already a real heavy, already, if you want, lattice structure that you put in here on the solution space. But it's even better because the prime agent writes now, given here the content of the planning phase, now the specific prompts for each agent. So all the sub-agent, the subtask are now defined and prompted and prompt engineered by our single prime agent. And here you see why this hub-and-spoke multi-agent system is not really, it's easy to code and it's easy to implement, it's easy to run, but it does not provide the best answers. Because it all depends here on the intelligence, on only one agent, and all the other agents simply depend on this one agent. And if you get this one wrong, oh buddy. Here we have some new research here from IBM, Zurich, Schweiz, ETH Zurich, hello Switzerland. And we are here eliciting reasoning in large language models with cognitive tools. And we here exactly, we could just continue. So what they tell us here, and you know that I told you here in the reasoning process, OpenAI almost always tries to rewrite here my human query into a Python code. And in that just uses here a solver to solve here my task. Either you have a math solver or you have Python or C++, whatever solver you have, it will not try to reason here in the human language because so many things could go wrong. So they say, hey, general tool use, especially if we have now MCP, beautiful. So use the right tool. LLM, do not try to think, which is absolutely fascinating. Yeah? And here IBM tells us here, June 13, 2025, hey, we developed 4 cognitive tools for reasoning. So this is not a code, also include, you have multiple tools for code, but these are cognitive tools for reasoning. And I love this because it shows you here the leading and bleeding edge of AI research where we are. We design tools for human reasoning. And here are the first 2 tools. So we have the tool to understand the human question. And now they say, we have here the cognitive architecture literature emphasizes the importance of a goal management and replicating here human reasoning. And it simply operates by breaking down a problem at hand to identify its key components. And again, we decompose a higher complexity into multiple lower complexity. And IBM tells us, hey, this is the understand the question tool. And then we have a recall-related tool, a cognitive tool. And this uses here the prompting technique, which consists of asking the model to recall previous knowledge to guide its own reasoning. So you say, hey, AI, do you remember for a particular task? In your pre-training, you were trained on a particular set of mathematical equations. Just now actively remember those equations, print out those equations, and they will form now the basis for your answering of this particular new human task. So it guides here the LLM through those examples, and it can now hopefully solve the question in hand. And then what I love is here, examine the answer given internally by the LLM. Ne? So you have a self-reflection step by the AI. The AI takes its first answer and says, hey, wait a minute, before I show this answer to the user, I will perform a self-reflection. I will check if there are the current reasoning traces. Are there any possible flaws? Is everything really watertight? Are there no wrong assumptions? Are there no miscalculation? Are there any boundary conditions, any constraints I did not take into account? So great. This is now a tool. Absolutely amazing. And then we have backtracking. And you notice from multicolored research. This is the multicolored research implementation in a tool. And you know what? You break it down into smaller steps, and those smaller steps, multicolored research, you got it. So now we have 4 brand new cognitive tools and our code tools and all the other tools that we have. And you know why? Because we want the AI to improve its reasoning performance. And it's simple steps, no? The AI should understand our question much better, given the context, given already some other answers the parametric knowledge of the AI already has. Examine, again, self-reflect on the answer, and do a multicolored research internally. Now, I want to show you here from IBM. This is from the IBM publication here. Really here, you shall use the cognitive tool. This is the prompt. And says, hey, you're an expert assistant for problem solving. You have access to a list of tools. You are encouraged to use tools when they make sense, when it's easier, clearer, more robust. Use your best judgment to decide when to call tools. And you say, oh no, this is the same wording. I do not say stupid wording. I just say the wording that Anthropic uses. You tell the AI to use your best judgment. This is exactly when I am standing in the morning in front of my mirror in the bathroom and I say, now, today, you will be beautiful. Yes, this is a different process. So yes, you tell the AI, hey, you may call tools at any point in your reasoning process. Only the tools listed below, and you give it here the 4 tools. And I want to show you an example. So the task is solve the math problem. Find the greatest common divisor by the 3 numbers. Beautiful. So what do you have? You have the tool, and the tool is defined here by the understand the human question prompt. And you tell the AI or the agent now, hey, you are an agent and you now design a tool or an MCP, and you are a mathematical reasoning assistant designed to analyze and break down complex mathematical problems into structured steps to help the system to actually solve problems. So we reduce the complexity. It's always the same pattern. To increase the intelligence of AI system, we have to reduce the complexity. Smaller parts, smaller pieces with lower complexity. Otherwise, the AI system fail. Okay, and those steps are, and we give it here exactly, no? Identify the core mathematical concept. Is it algebra, calculus, linear algebra? What is it? Extract and categorize the relevant symbols, the variables, the function. Just tell me what you see, what you can identify. 3 is especially important. Rephrase now the problem into a step-by-step sequence to make solving easier. So you say, before I start to do anything, just let's rephrase the mathematical task. Try to find a step-by-step sequence solution. We use some methodology that we can identify in the 10,000 GitHub repos that we have been trained on. Then we highlight any known theorems or techniques that we found that is useful for this problem. And do not provide any answer to the question, only provide instruction which will guide the upstream system. So you just want to make sure that the human text is now reinterpreted and rewritten here internally by the AI for the AI to increase here the chance that it can solve this. And here you have now the answer. If you execute this, this is what you get. So for this particular mathematical problem, no, problem analysis, core mathematical concept, the problem involves finding the greatest common divisor of 3 numbers, which is a fundamental concept in number theory. Second, extract and categorize relevant symbols. Beautiful. Point 3, rephrase the problems. Find the prime factorization of the numbers, identify the common prime factors among the 3 numbers, multiply the common prime factors together to find the greatest common divisor. Beautiful. Known theorems and techniques. Euclidean algorithms can be used, prime factorization, step-by-step instruction. This is what we have to do. And you see, we have now the LLM performing here the planning, the strategy. How will I solve this? It executed not a single step operationally. It was just thinking, what is the best way to solve it? Therefore, thinking models are beautiful. And then you have maybe a code, and then you go on, and then you activate all the other agents, and all the other agents have the possibility to activate their tools. And this is a cognitive tool, and you have cognitive agents, and you have multi-agent, and you get the idea. And if you have now a recall-related prompt, this is your self-reflection. But you know what? If you see here that the AI generates out of its parametric knowledge in-context learning examples, few-shot ICL examples. So we have here, and we tell the AI, hey, listen, AI, I just want to make sure that we are both here on the same page, no? So show me now in the output format here 3 examples that are really similar, so I really, as a human supervisor, understand that you understand the problem, that you are really able and you have been trained and you know how to solve this particular problem. So show me your in-context learning examples. Absolutely fascinating. So you see, IBM is trying here to define the reasoning process right from the beginning, to optimize the reasoning process by making sure that the LLM understands the human query. And it is not a vision language model, vision language action model, or robotic model. It always comes down to the core nucleus of a large language model that does the reasoning. And they want to make sure, understand the human query in context and in the given details, given here the specific pre-training domain knowledge of this particular LLM, or if you want to see my last video again, activate here the reasoning agentic RAG system if the LLM decides, hey, I need external knowledge, I need to connect to an external database or external GitHub repo, or external physical numerical simulation agent, or whatever. So you see, it all comes together. RAG, agentic, reasoning. Reasoning is the core, the most important topic currently in AI. And you might ask, hey, wait a minute, but I have here, as I have seen here, by Anthropic just in last video, cognitive prompting. Why is a prompt not enough? Why we have to go to cognitive tools now? And even if we have the beautiful MCP and agent-to-agent communication protocols, what is the difference between prompting and tool use, especially for large reasoning models? Now, the authors tell us here, well, our work is here based on the idea of cognitive prompting by complementing insights from cognitive psychology and theoretical neuroscience. And we have the idea that modularity might be important and fundamental. Great. And they say, a modular approach has multiple benefits from the prompt engineering perspective compared to a monolithic prompt approach. Modularity helps the LLM focus on implementing the specific cognitive operation, it's a neural network, at hand, in isolation from the rest of the context windows that has been provided so far. So who is doing this? IBM. IBM is coming up and telling us, we want to reduce the cognitive load of an agent, of an LLM, and therefore we go here with a tool approach and we do not integrate this in the monolithic prompt in the context window. And second, they say, hey, this is encourages here the flexibility. We do not enforce here the model to use a predefined order of tool calls. Yes, Anthropic does it. See my last video. To solve the query, it's absolutely free to the AI, what the AI wants to do, what tools it wants to call, at what time, what specific tool, And this is in contrast with cognitive prompting, which directly provides here the LLM with order of steps it needs to follow the given problem. And you immediately recognize, hey, this is exactly from yesterday's video, because we had agentic reasoning for the RAG system here. And we said we have 2 kinds of solution. We have a prompt-based, hard-coded solution, and this is Anthropic. And we have a pure training-based solution when the LLM decides itself, given its reinforcement learning procedures. So you see, beautiful IBM, more or less published here on the same date, gives us here the same basic understanding of prompt-based agentic reasoning and training-based agentic reasoning. So nice. Let's come to the result. Does it have a benefit? So the baseline, if we use here Q1 2.5 or 32B, Llama 3.1 or Llama 3.3, the baseline numbers are those. And then we do the cognitive prompting. And you see the performance goes down, which is interesting. It goes up, goes down, goes up. But interesting is, of course, the delta between the cognitive prompting and the cognitive tool use by IBM here. And IBM tells us here, look, this is the best, this is the best, this is the best, and this is the best. So cognitive tools are now preferred over cognitive prompt engineering, cognitive prompting in general. Interesting insight. Learned this today. Now, we talked already about mixture of experts system, and here, June 13, 2025, we have here, Fudan University, beautiful question, and they say, hey, very innocently, they ask, hey, are mixture of expert system not the better core of an AI agent than a dense LLM? Is it not, I don't know, computationally or energy specific better to have a mixture of expert system than to have a dense LLM? And this is a beautiful study. I highly recommend. And yes, you will find the answer here in this study. And there's a new study also, June 14, 2025, by Google DeepMind. And they examine here this rethinking example here. And Google tells us here, hey, we demonstrate that longer context, 2 million context length, can accommodate now more examples, especially if we talk about in-context learning. We just talked about this 2 minutes ago. So we can increase the number of ICL demonstration, but don't make the mistake as a coder that you think that if you put 1,000, 2,000, 3,000 ICL few-shot examples into the prompt, this will not guarantee an improved performance. Because what you do is you just hope that in those 2,000 examples, there's also a high complexity topic, a high complexity solution that will help your system to become, quotation mark, super intelligent. But you know what? In general, from the internet, from GitHub, you find ICL demonstrations that have more or less all together a very low complexity. So if you have 100 low complexities or 1,000 low complexity few-shot demonstration examples, it will not improve the performance on higher complexity tasks. Very nice study. A lot of data. Have a look at this. And they develop here refract in context learning. And they say, what was specially here, have an algorithm designed to focus here the LLM attention on challenging examples, on higher complexity examples. We have to filter out, these real simple, trivial solutions we are not interested in. If we do ICL, we want to do it here on the real challenging examples. Beautiful. Of course, we have to talk about the RAG. No, absolutely, you might say. And you see here, and this is nice because this is the first study I see here from organizations here in Thailand, Bangkok, Thailand. Hey, welcome. Great that you have some publication. And they introduce here dynamic of sort aggregation RAG system. But why I want to show this to you is they also, the query rewriting. They do not accept the human query as given. They say, hey, our system will rewrite the human query according to what our system knows, because the RAG system have to improve here its performance, and we do this with a query rewriting. So have some fun, check, ask your system, hey, how did you rewrite my query, my task description? What is your internal representation now of my human query? Yeah, and they say, well, we have some problems, and one of the 3-stage pipeline that we define now, first step is rewrite the human query. But I know you all have been waiting here for the next step, for the superhuman intelligence. Well, of course, and I love it when I see here, this is here from June 13, 2025 by Google DeepMind, and they have here for LLMs now, there's a new way to help humans learn the potentially superhuman concept of LLMs. When I read here the superhuman concept of LLMs, I don't think about marketing at all. No, because this is here science. No, so let's have a look at superhuman, the cognitive decomposition and the superhuman AI. And yeah, you can imagine what it is. But what I want to show you, and this is a study here by June 16, 2025, also by Google DeepMind, but this is a complete different level. If you want, this is the paper of today. Because here we're talking now about what happens if our AI system become more and more complex and are able to solve more and more complex tasks. Will there ever be a limit to this? And they say here, training powerful AI system to exhibit a desired behavior hinges here on the ability to provide accurate human supervision on increasingly complex tasks. Because if you just tell an AI, hey, do it yourself, just increase the complexity above your current level, and I do not give you new human data that are on a higher complexity level, I just tell you, hey, synthesize your AI that is limited by the current complexity level, synthesize new training data that go beyond your current pattern recognition capabilities, just do it, the system will fail. So you need a human supervision or a human guidance or you get the idea. And they say, hey, this is a promising approach to this problem is to amplify the human judgment by game theory. So if you are into mathematics, this is a beautiful paper for you. And they say, there is now a critical problem with scalable oversight. Because how to provide accurate training supervision, the pre-training of the LLMs that have a higher complexity potential to solve here, such that these powerful yet opaque AI systems behave as intended, even when their tasks are too complex for direct human understanding and verification. So they say now, hey, our systems will soon be so complex in their training procedures. But we understand we need a human oversight, a human understanding of the processes, and a human verification that the AI systems are really doing what we as humans want. So we run into a problem because the AI will become too complex for human understanding. And they found a beautiful solution, and the solution is here from computational complexity theory. So if you have a PhD in mathematics and you are an expert in computational complexity theory, you're gonna love this paper. Because they prove here that a computational limited human brain, like my little brain, can suddenly judge here the correct solution to problems of much larger computational complexity, like the new AI system, by observing now, and now the solution is a structured debate between two computational, much more powerful AIs, like I as a human are. So they say the main idea now that we have still the human in the loop, if the system become extreme powerful, is a human watches a debate between two AI systems. And the human just watches the augmentation of the two AI systems. One is pro, one is contra for something. And now they recursively break down here a complex problem, a high complexity, again, the same pattern, into simpler sub-problems with a lower complexity. So you see, this is our main pattern. How we increase the intelligence in AI is by reduce the complexity and breaking down in simpler sub-problems and multiple problems. And then we hope that any AI is able to put all those sub-problems and their solution back together, which we have not shown at all that it is working, but this would be the topic of another video. So we watch here the two AI systems debate as a human with my little brain, and eventually terminating in sub-problems that are simple enough for my little brain, for the computational limited human, yes, okay, it is me, I got it, to judge now these two overwhelmingly computational powerful AIs directly. So I can now, as a human with a computational limited brain, decide which of the two AIs are telling me the truth. Now you see, computational complexity theory meets game theory. And yeah, this is here a little bit of an explanation if you want to understand what I'm talking about here in more detail. If you have here two systems, and one is here a debate system that acts here as a code reviewer system, and you see, just watching or listening to their discussion, Google says, hey, you as a human, you can decide which of these superior AI system, the one that is lying to you and the one that is telling you the truth. And the idea is you just watch them talk and reduce the complexity and reduce the complexity and reduce the complexity. And then suddenly we are at a level that a normal human intelligence, yes, this is me, can decide which system I'm gonna trust. Or is it just playing me here that I start to trust it and then it turns on me? So absolutely fascinating what Google is currently exploring, how to judge the system that they are designing in the future, but that a normal human intelligence working at Google and you only have 3 PhDs, how is this human able to judge which of their superhuman AI is lying to the humans? I think it's absolutely fascinating what we have currently as a topic in AI research, because now we are going here from cognitive science here to game theory, computational theory, complexity theory, numerical theory, computer science. Amazing. And they provide here a theorem of completeness. And this goes an honest prover in superior AI intelligence who currently provides here a stable decomposition into solvable subproblems. And again, we have here higher complexity is reduced to lower complexity. This honest prover can always win the debate against the bad other AI that has a dishonest estimator. And they start here, of course, here with an alpha approximate Stackelberg equilibrium here in a strategy profile. So if you like this kind of topic, then read the study. Otherwise, maybe just do as I do. And I say, hey, they have proven the existence of a stable decomposition of a higher complexity into solvable subproblems with a lower complexity. And as for today, I'm happy with this. Maybe at the weekend, I would like to have a deep dive. So, you see, we are talking more about superhuman AI, but really on a deep mathematical level, we're trying to understand how can we keep here the context between what human design a new AI system and how we can keep, I don't want to say control of this system, but how can we make sure that we understand at least a little bit of a fraction? Are they lying to us? Are they deceiving us? Are they telling us the truth? And we run into theoretical problems that are just amazing to solve. And I think Google here in the last week published some amazing papers, some amazing AI research papers, especially on the topic. And you can see quite clearly where we are moving here into the very near future. And I think it's just amazing time in AI. If you subscribe, I guess you will see more of this kind of video.